increasing and decreasing function. A function is increasing on an interval I if the function f of x1 is less than f of x2 whenever x1 is strictly less than x2. Notice here when increasing, we could be equal for different x1 and x2s, but the second point will never be less than the first point. So if we draw a graph and we have a line of some sort, this would be increasing. These points here, the function's never smaller. It could be equal, but no matter which points you have, if you take the second point and then subtract the first point, so our second point and then subtract the first point, the second point will always be at least as high as the first point. And a function is an increasing function if this is true for all x in R. So if we look to highlight the difference here, let's look at the function x squared and the function that we had. This function here, for any x values, this is true. Whereas here, as long as I am greater than 0, x squared is increasing if x is greater than or equal to 0. That's where x squared is increasing. Right? And similar to increasing, we also have decreasing. The function is decreasing on an interval I if the first point is higher than the second. Right? So if we take a function and we take 2 points, the second point, the point with a larger x value or more positive x value, will have a smaller output than the function, than the point before. And the function is a decreasing function if this is true for any x in R. Okay. Now here, this is a decreasing function. This is an increasing, so decreasing. This is increasing. But here, x squared is decreasing if x is less than or equal to 2. Now, if the inequality on the function is strict, meaning f of x is strictly greater than f of x2 is strictly greater than f of x1, we add the adjective strictly. For example, a function is strictly increasing on the interval I if f of x1 is strictly less than f of x2 whenever x1 is strictly less than x2 in the interval I. Now we have some practice. First, we're going to show that f of x is increasing and decreasing. Show that f of 5x is strictly increasing. Show that x squared is not an increasing or decreasing function. And determine over which interval it is increasing and what interval it is decreasing. And finally, show that f equals minus 3x plus 2 is a decreasing function. Highly encourage you to go through this process. One thing to comment here is some texts define this slightly different. Strictly increasing is what they call increasing functions. And a function is not increasing if it doesn't have this strict inequality. It's sometimes defined slightly differently in other contexts. But as you go on to study calculus, the definition that you will use will be clearly given. Now that we've looked at some properties, we're going to look at two special functions, our exponential functions and our logarithmic functions. The function f of x equals a to the x is called an exponential function. And here, a is a real positive number. That a must be a positive number for our exponential functions. Now, here there's three different exponential functions based on the values of a. We have a less than 0. We have this, as we go backwards, it goes up. As we go forwards, it goes to 0. We have a equal to 1. It's a straight line. And if a is greater than 1, then as I go to the left, I go to 0. And as I go to the right, I go up to infinity. And notice that all three functions cross through at the y-intercept of 1. Now let's summarize these end behaviors. Well, if a is less than 1, then the right end behavior, f of x, approaches 0 as x approaches infinity. And the left end behavior is infinity. So f of x approaches infinity as x approaches minus infinity. When a equals 1, the right end behaviors are both 1. So f of x approaches 1 as x approaches infinity. And f of x approaches 1 as x approaches minus infinity. Now, when a is greater than 0, f of x approaches infinity as x approaches infinity, or our right end behavior is positive infinity, whereas our left end behavior is 0. So f of x approaches 0 as x approaches minus infinity. Now, computing x changes depending on the value of x. In the 0 exponent, a to the 0 will always be 1 for all. This is true for all a greater than 0. For positive integers, it's a times a times a n times. And for negative integers, it's 1 over a to the positive n. Now, if we have a rational exponent, then it's going to be a to the power p, and then the qth root of that number, or the qth root of a to the power p. Now, in both cases, the qth root of a to the power p. Okay. Now, in order to get an irrational exponent, we're actually going to take a limit. And this is similar to what we discussed before. It's the limit as q approaches a of f. Oh, let's explicitly define it. Of a, or as q approaches x of a of q, where q is a rational number. Now, the way in which this limit works will be defined if you take a more proof-based math course, like A31, but for A30 or A29, this won't really be discussed, if at all. And with our exponential functions, we have our exponential rules, which we discussed before with our power rule. A to the x times a to the y is a to the x plus y. A to the x over a to the y is a to the x minus y. A to the x all to the y is a xy, and a to the x a to the x b to the x equals a b to the x. Now, this base, this real number can be anything, but there's a really useful base. And it's such a special base, we give it a name. Sometimes we call it the Euler's constant. Now, the Euler's constant E is an irrational number. But why is it so important? The importance will be seen when you explore derivatives. You'll see how nice and pretty it is when we explore derivatives. Now, connected to the exponential function is our logarithmic function. And if we let a be any real number, positive real number, where a does not equal 1, then log a of x is called a logarithmic function. And the logarithmic function is the inverse of the exponential function. And we'll talk about that later. But what it means is that log of a of x equals y, if and only if a to the y equals x. And here, if we'll explain why later, but we only have two options. We have a less than 1 and a greater than 1. And if a is less than 1, we get this shape here. And if a is greater than 1, we get this nice shape here. Note then when a equals 1, log of a of x is not actually a function. This is the vertical line x equals 1, which is not a function. It's a line, but it's not a function. Now, similar to our exponential function, where we have exponential rules, we have logarithmic rules. The logarithmic rules that we have is that log base a of ab equals log base a of a plus log base a b. Log of a divided by b is equal to log base a minus log base a b. Now, log base a to the power n equals n log base a, where n is any real number. Using this, we're going to compute what this expression is. So log base 2 of 24 minus log base 2 of 3 is equal to log base 2 of 24 over 3 by rule 2, which is equal to log base 2 of 8. Now, 8 is 2 to the 3. So this equals log base 2 of 2 to the 3, which equals 3 log base 2 of 2. Now, log base 2 of 2, we ask ourselves, 2 to what number gives me 2? And that number is 1. So 2 to the 1 equals 2 implies that log base 2 of 2 equals 1. So this equals 3 times 1, which equals 3. And now we get our natural logarithm. Now the natural logarithm is based on that constant we talked about before, that constant e, which is super important. The natural logarithm is a logarithm where our base is that nice number. And we use ln to represent the natural logarithm. This can be said as ln of x or ln x. It can be ln of x, or it could be natural logarithm of x. This is the one we typically use. We typically will be saying ln of x. And we have a nice change of base formula when using our logarithms and exponents. And one of them is really nice and one of them is not so nice. So the really nice one is this one here. This is our really nice change of base. That log of a of x equals log of b of x over log of b of a. This one we use lots, and we will discuss this when taking derivatives. Whereas this technique here has some uses, but not many. There are some uses, but not many uses. The change of basis formula for exponentials is rarely used, but the change of basis for logarithmics is used all the time, especially when we get to derivatives.